All right, so let's delve a little deeper on the state postulate. So let's recall that the state postulate says the following. The state of a quantum mechanical system is a normalized vector in some appropriate Hilbert space. Now, the state for a qubit is just the Hilbert space for a qubit is just C2. So for a qubit, the Hilbert space is C2, and the state ket psi is a linear combination of ket 0 and ket 1, and alpha and beta are complex numbers where mod alpha square plus mod beta square is equal to 1. All right. So, the other thing to note is that if I have a state ket psi, then I this is equivalent to the state e to the I phi psi. So this is known as a global phase, and due to the measurement postulate, these states can't be really distinguished in terms of measurement. So therefore, these two states are not the same but are equivalent. They are indistinguishable in terms of the measurement. All right. So now there is a very nice way of visualizing the a qubit, and it's called the Bloch sphere. The Bloch sphere is actually a sphere, and on the surface of the Bloch sphere, you have these pure states, which can be visualized very nicely. So let's say you have uh, a sphere. Let me draw this Bloch sphere. So this is a sphere, and then okay, so we have okay, so I've drawn a sphere. So on the surface of the sphere is are all the pure states. For instance, the north pole will be this ket 0 state. The south pole will be ket 1, and so on, right? This is a sphere. So let's say this is a unit sphere. So we have x square plus y square plus z square is equal to 1. And if I have any point on the sphere, let's say, let's draw a point. We have, let's say, a point. Then let's go to spherical coordinates. And this point can be represented in terms of these angles. So this is called theta. Uh, and then this angle over here, it will be phi. So this angle will be phi. So the if you go to spherical coordinates, then it will be cos. So x will be cos theta and cos phi. Y will be cos theta sin phi, and z will be sin theta. Okay, so we are going to go to polar coordinates, and so any point on the Bloch sphere is a pure state, and the state which is given by the angle theta and phi. So well, theta will run from pi 0 to pi, and phi will run from 0 to 2 pi. Then the state psi is given by cos theta over 2 ket 0 plus e to the I phi sine theta over 2 ket 1. So this state over here, which has the coordinates cos theta cos theta sine phi, and sine theta, uh, represents a quantum state that is given by this state. So this is equal to cos theta over 2 and e to the I phi sine theta over 2. This state will be um, this point on the Bloch sphere. So this point is given by the point that is I just drawn the point. This will be the state on the Bloch sphere. Now, let's see why this has to be true. So the reason is due to what I already mentioned, that one is unable to distinguish between a state and the state which is multiplied by a global phase. So let's try to show that this Bloch sphere representation is actually correct. So let's think of a general state. So a general quantum state, a qubit, can be represented as alpha times ket 0 plus beta times ket 1, where alpha and beta are complex numbers, and mod alpha square plus mod beta square is equal to 1. So let me change to the complex numbers can be written as R alpha times e to the I phi of alpha 0, right? So this is the polar form, and then this is R beta times e to the I phi of beta ket 1, right? So alpha is a complex number which can be written as R alpha e to the I phi alpha, and beta is another complex number which can be represented as R beta e to the I phi beta. Okay, so now I can take e to the I alpha outside, phi alpha outside, and then this is R alpha ket 0 plus R beta into e to the I phi beta minus phi of alpha. So now this is a global phase. So one can remove 1 degree of freedom by ignoring this global phase. So phi, I'll call it phi prime, is equivalent to phi, or rather phi is equivalent to phi prime, which is equal to R alpha ket 0 plus R beta e to the I phi alpha minus phi beta ket 1, right? So I can write this is a complex number. I can write this complex number as x plus iy. So therefore we get R alpha square plus x square plus y square is equal to 1, which is the surface of a two sphere or a sphere. So this is surface of a sphere. And I can write R alpha to be cos of theta, and I can take x plus iy as e to the I phi sine of theta, right? Because of this condition that psi is a normalized vector. And then I can write psi prime as cos theta plus ket 1, ket 0, sorry, ket 0 plus e to the I phi sine theta ket 1, where this e to the I phi is actually equal to e to the I phi beta minus phi alpha, and r beta is sine theta. So because of this normalized condition, I can write this. So this is, and therefore we get z is equal to cos theta, r alpha is equal to z. Then I get x plus iy is equal to e to the I phi sine theta, which is equal to cos phi sine theta plus I sine phi sine theta. So therefore we get x to be equal to cos phi sine theta and y to be equal to sine phi sine theta. Right. So therefore the qubit can be represented on the sphere, and the qubit is cos theta ket 0 plus I e to the I phi sine theta ket 1. And the only problem is that if we let theta, which run from pi to 0, then for theta equal to 0, you get for theta is equal to 0, we get 0. And for theta is equal to pi, we get uh, minus so when theta is equal to pi, or rather pi over 2, right? Say, so when theta is pi over 2, so this itself, we'll get e to the I phi times ket 1, which is equivalent to ket 1. So the reason we add this theta over 2 factor is because if we just let theta run from 0 to pi over 2, we'll cover the entire qubit space. So, and it will be only the hemisphere. So the entire qubit space will only be the half sphere or the hemisphere. And therefore, instead of uh, theta, we have this theta over 2 factor over here. And so therefore, this is the state of a qubit on the Bloch sphere.